All right, this is video number 2 for section 3.2. We're going to continue looking at some different properties and characteristics of the graphs of a polynomial function. Okay, we're going to scroll over to where it says local extrema, and we're going to review this concept that we saw in an earlier chapter. Local extrema are referred to as the turning points of your graph. It's where your graph changes direction from being an increasing function to a decreasing function, okay? These are often referred to as local maximums and local minimums, right? So here you have an example of a function that is, this is a quartic polynomial function, and notice it has 3 turning points, okay? 3 turning points. Up at the top here, this point would be considered where your local maximum is taking place. Remember, it's just referred to as a local maximum because it's not the highest point of the entire function, okay? It just is in that small localized area. Similarly, this point right here would be where your local minimum is occurring. And then down at the very bottom, this is your absolute minimum. It's absolute in the fact that this is literally the lowest point of the entire curve, okay? Now, we're reviewing this concept because we need to be able to know how many turning points a graph has or a function has for us to be able to graph it, okay? Understand we're not going to have enough knowledge base to be able to identify the exact locations of these turning points. If we're only given the equation of the function, we won't know these exact values for our local extrema until we learn some calculus, okay? So that's what you would be doing as you move forward into calc, okay? All right, next let's refer or talk about the roots and multiplicity of a function, okay? So let's say f is our function and r is a real number so that when you evaluate the function f with r, it equals 0. That means r is considered to be a real zero of the function. And a real zero of a function is the same thing as the x-intercept of the function, okay? That means r is an x-intercept, and it also means that x minus r is going to be a factor of the function, okay? Now, in terms of vocabulary, you have a lot of words that typically mean the same thing, okay? So if you hear the words zeros, x-intercepts, or roots, they're all synonyms of one another, okay? So they all essentially mean the same thing. Where's the function touching or crossing the x-axis, okay? So notice the function that's given here, f of x equals 2x cubed minus 10x squared plus 4x plus 16. So I've given it to you in its expanded form, and then below I've also given it to you in its factored form, okay? The expanded form is really good for identifying the degree of the function. The degree is 3, which is just, again, the highest power of the function. And then the factored form is really good for identifying the roots, okay? So we know if I take each of these factors and I set them equal to 0, they're going to lead us to our roots. They would be at x equals -1, +2, and +4, okay? Now let's refer to the multiplicity of a root, okay? When a function has a factor repeated n times, we say that the corresponding 0 or the corresponding root of that factor has a multiplicity of n. Okay, so basically the power on the factor tells you what the multiplicity of the corresponding root is. Okay, so for example, in the function f of x equals x minus 1 times x minus 4 to the third power times x plus 2 squared, the root of 1 has a multiplicity of 1. That's because the root of 1 is coming from this factor whose power is 1. The root of 4 has a multiplicity of 3, and that's because 4 is coming from this factor whose power is 3. And then the root of -2 has a multiplicity of 2. That's because the root of -2 is coming from this factor, whose power is 2. Okay? Now, I want you to notice that if you add up the multiplicities of all of your roots, they're always going to add up to the degree of the entire function. Okay? So if I add up the multiplicities of 1, 2, and 3 from the previous example, that's a total of 6. That means this function is going to have a degree of 6 to it. Okay? All right, now how does this relate to graphs? Okay, well, let's take a look here at investigation in Desmos. Okay, all right, so basically you can see I've got in box 2, I have a function that has several factors to it. It's in its factored form. And I have the powers on each factor set to be sliders so that we can adjust the values of them, okay? So notice the first factor is x plus 3. That means it would have an x-intercept at -3, or root at -3. Then we have x plus 1, root at -1, and we have x minus 2, root at +2, okay? And notice right now I have all 3 sliders, so the values of A, B, and C, they're all set to 1, okay? So let's focus right now on the slider for A, which means we are playing around with the multiplicity of the root for -3, okay? Let me move A up to 2. Okay, so notice how that changed the graph, okay? Now at the root of -3, the graph is behaving kind of like a parabola, okay? Let's move it to A equals 3. So when the multiplicity is 3, at x equals -3, the graph is now behaving cubically. Now the multiplicity is 4, at x equals -3, the graph is behaving kind of like a parabola, but really it's more like the power function y equals x to the 4th, okay? And let me go back and do the same for some of the other roots. So let's focus on x plus 1. Its root is -1. So right now at -1, you're behaving like a line. Then if I raise the power to 2, where the multiplicity is 2, now we behave like a parabola. Then at -1, when the multiplicity is 3, we behave like a cubic. Back to more like a parabola. Hopefully you're catching the gist of this, okay? So let's formalize this. Basically, we can generalize it to the following. Roots of even multiplicity result in a graph that touches the x-axis. So what I mean by touches is something like this. Your curve is doing that. Okay, that particular root would have to have an even multiplicity. Okay, roots of odd multiplicity result in a graph that crosses the x-axis at that root. Okay, and what I mean by that is, so let's say we have an odd multiplicity of 3, then that means the curve's going to do something like that. It's going to behave cubically and cross through the x-axis. Okay, now we can take this a step further and we can say the root of multiplicity n will behave like f of x equals x to the power of n near that root. Okay, so the fact that in this last sketch that I did that it was behaving cubically, that tells me we're behaving like y equals x cubed. The multiplicity was 3. And then up here, we could maybe say this behaves like y equals x squared because the multiplicity was 2, okay? Some other properties associated with the powers on your function, okay? So a function of degree n has at most n unique real zeros, okay? So this just kind of piggybacks off the fact that the multiplicities of all of your zeros, all of your roots, they have to add up to the degree, okay? So if your degree is 6 for your function, you're never going to have more than 6 zeros to the function. That's what that's stating, okay? Could you have fewer than 6? Yeah, there could be fewer than 6 unique real zeros, but that would just mean that some of those zeros, they'd have to have a multiplicity other than 1. Okay. Um, Also, a function of degree n has at most n minus 1 turning points or local extrema. Okay. Once again, I want to stress the word at most. So let's say your degree is 4. That means you're going to have at most 3 turning points to the curve. Could you have fewer than 3? Absolutely. It's just going to depend on multiplicities on all of your roots or zeros. Okay. All right. Now you're going to go over to practice 2. I want you to pause the video, work through that yourself, and then come back and check your work with mine just to see if you got this concept down.